So initial conditions have their own name list. The hydro conditions and the magnetic conditions are initialized using two different flags. Okay, so init type, whenever we set that flag, that's referring to how we want to initialize the hydro. Whenever we set the magnetic init type flag, that's telling us how we want to initialize the magnetic field. Okay. And so typically, when you're initializing these things, if you're not doing one of these benchmarks, you just want to give it some random thermal field to get the convection going, and you want to give it some kind of random magnetic field. Okay, so that's what this example does. So 7 is the code for the random thermal field and the random magnetic field. And then there's an amplitude here, which basically tells you the maximum amplitude of those random perturbations. And that amplitude, I should say, is per spherical harmonic mode. So the integrated amplitude across all the spherical harmonics could be different. But they're initialized, the power in the different modes is randomized, and the phasing of the modes is randomized. Okay. So that's the one I use quite a bit. This initializes a zero velocity field. So velocity just responds to whatever you've given it for the thermal field. For fixed temperature boundaries, it's fairly common that you may want to randomize the thermal field, but you want to make sure that the spherically symmetric temperature entropy profile is conductive. Okay, so if you want to do that, you just set this little flag, conductive underscore profile equals true. That randomizes everything but the spherically symmetric component. Okay, so that sets it to something that's in conductive equilibrium based on your boundary conditions and based on any internal heating that you have in your problem.
So in the documentation, there's presumably like a list of all these different things.
Yeah, there will be. The documentation is still kind of...
There's a directory there.
Yeah, that one is really more about getting the code up and running. Yeah. But please email me.
So but the other point, I guess, is if you start sort of digging through the code, is there enough documentation in the code that you would also...
Yeah, you should be able to. I mean, I commented it, fairly well. So yeah, you should be able to kind of tell.
You can find a defaults list.
Yeah, probably. I mean, actually, the most useful thing, I can kind of point people to a few of these since the question came up. Let's go back to the Rayleigh directory itself. And within Rayleigh, we'll go to the physics directory, and we will edit controls.f90 with a capital C in physics. Then depending on how your text editor does things, this will look nice or it won't look nice. But these are, a lot of these are the flags that we've been going over. There's some flags here that you should never touch. Static transpose, static config, those are advanced user flags. But here's, for instance, are the physics flags, the benchmark, report and integration interval. And I try to provide some comments on what everything is. I did want to point something out since we're here. I noticed I tend to specify CFL min and max in my input files, and I just noticed that my default is flipped. So you should specify those yourself. This kind of does something a bit odd. I would imagine. I always specify it. Separately, if we look in that same directory in boundary conditions.f90, you can see the available flags. Though I didn't comment these because they're fairly self-explanatory. There is another magnetic field boundary condition, but I wouldn't really use that one right now. It's a bit specialized. And then the other place...
And you do solar cases, do you have to match the potential field?
You do a match like the solar, like a solar observed field? No, it's not that sophisticated. And there was one other spot here, initial, and then an initial conditions.f90. Yeah, I guess here there's not as much, but there are some descriptions further down. You can kind of see what's being called for the different init types. Okay, and it prints some stuff. So that's actually printed at runtime too. So that's typically the way you want to initialize things. It is worth noting you can restart from a hydro case. So init type -1, but you can start an MHD simulation from a hydro case. So you can just toss in some random magnetic field into an equilibrated run. So that's an example of how to do that. You can also restart both, which is usually what you would be doing. Set them both to -1. They restart from the same checkpoint. You can't restart the magnetic and the hydro pieces from a different checkpoint file. They'll always restart from the same checkpoint or one. It's just randomized. And then there's several other init types which are reserved for the benchmarks. And so the best thing to do is to just see the input examples for the benchmark runs. And so we'll kind of continue on. Why don't we try to initialize a random thermal field in our Boost case? Okay, so right now it was set for the benchmark setup, which initializes a sectoral mode, basically. So let's randomize that. But in so doing, we need to make sure we set the conductive profile flag, okay, so that our initial conditions agree with our boundary conditions.
And so this is not case sensitive. It's not case sensitive.
No, that's a good question. The input files are not case sensitive. Yeah, Python is case sensitive. So we're gonna come back to these when we do some plotting. All right, so pretty simple. Just you can set your flags. I probably forgot conductive profiling when I didn't. And then let's do one more modification of this. Let's add magnetism to this. So we'll turn magnetism on in the physical controls name list, and we'll initialize a randomized magnetic field. So I would turn magnetism on here. And then I'll give it a magnetic init type 7. And a mag amp. I'm trying to remember, what's the magnetic amplitude in these benchmark runs typically? Do you know?
10⁻2 or 4.
So that, okay, so we'll just do something small, so like 10⁻4. You want to make sure you don't give it too large of a perturbation. So I'll run that, and I have some messages here that say I've got a random thermal field and a random magnetic field. All right, so that's boundary conditions and initialization. And now I'm going to move into talking about reference and background states, okay? So there's another name list, the reference state name list. And if you look at these 3 different cases we have, you'll notice they all have a different reference type, okay? The reference type is telling us, are we doing a Boost run? Are we doing an anelastic dimensional run? Or are we doing an anelastic non-dimensional run, okay? And so each type of run is controlled a little bit differently. So why don't we... Yeah?
So the Boost case is a non-dimensional.
That's right, yes. Sorry, I should have said that. Yeah, Boost is non-dimensional. The only thing that's dimensional is reference type 2. I know most people don't run dimensionally. So anyway, yes, Boost is non-dimensional. So let's look, for instance, at the main input in the Boost directory. Okay? And so we solve the Boost equations. These are the equations that are being solved. Modulo typos, I think I've got everything right there. So I non-dimensionalized mine using the thermal diffusion time. Okay, if someone feels really strongly, I'm going to have a custom reference state set up soon. It's interesting. Actually, I was just describing it to Mike Hawkins, and he says Calypso has this. So you can just set the coefficients in the equations to whatever you want. But for now, this is the non-dimensionalization
That's also the most confusing part of it.
Yes, right.
I mean, it may be if we found out that people had sort of 5 or 6 standard non-dimensionalizations, like just add them into the code as reference types. But anyway, if you look at your name list, your reference state name list, you'll see a lot of these things are set, right? So, and they're just spelled out: Prandtl number, Rayleigh number. Should be pretty obvious. Gravity power is this little n on the gravity here, so you can have constant gravity in this setup, or you can vary as some function of radius. It's normalized by the outer boundary. I think that's really all there is to that. Are there any questions on that? So now, if you were to go over to the anelastic directory, not the anelastic ND, but the anelastic directory, that's setting up dimensional anelastic run. And this is the equation set being solved. Okay, it's pretty standard. But the difference here, right, is that we have coefficients that are allowed to vary in radius, right? And this depends on here we work in the Lance-Brzezinski-Roberts approximation. I don't know if you're familiar with that, but in essence, you assume that your reference state is adiabatic. That allows you to write your pressure and gravity terms this way. That's why you have this P grad P over rho bar, where rho bar is the reference state quantity. That's set with reference type 2, so you'll see that in the main input in the anelastic directory. Okay, and this one takes two name lists to control. Okay, you got the reference state name list where you specify. So it uses I should have said this. It assumes a polytropic background. Okay, you can specify the polytropic index, the number of density scale heights, the mass interior to your convection zone. Okay, so this was a solar simulation. So this is the solar mass. This is, by the way, the dimension, when it says dimensional, it's in CGS units. Yeah, I should have said that. It's probably obvious if you look at the equations here, but you don't see mu naught floating around. But anyway, you specify the rotation rate here in the reference state name list. You need a specific heat at constant pressure. And then separately, there's a transport name list at the bottom, and this allows you to set new kappa and eta, your diffusion coefficients. Okay. If you want to get a feel for how this is working, you can see this paper from earlier this year. Basically, it is this setup without rotation. Okay, there's several runs set up here. It discusses the background state. The background state is also discussed in the Jones benchmark paper. It's the same kind of setup. Okay. Any questions? Here it's kind of like look at the examples and sort of modify.
So you specifically identifying these top, do they vary with the density or something?
That's a good question. You know what? Tomorrow night I'll make a slide or two that show you. These are constant by default, but you can make them vary with density if you want. And I'll include a slide with that tomorrow night to show how to do that. Yeah, because it's assumed that if you look here, right, eta is inside the curl. Eta is allowed to vary. Nu is inside the divergence operator. They're all allowed to vary with radius. Okay. And then the anelastic non-dimensional setup, which actually we're going to have MHD in there soon. I need to consult with Moritz this week to make sure I haven't goofed something. But this is similar to what's done in Magic, and so it also assumes a polytropic background. You access this with reference type 3, and you have a series of non-dimensional numbers that you need to specify. So there's not a lot there, but you can see this paper from Nature Geoscience from this year to see like this is actually the run from that paper, though the resolution might be a little bit less than what it needs to be. But this is how you set that up. Okay. Is it alpha in order of magnitude? Yeah. Okay. Okay. Well, Other than that, so just the resolution is poor. I'm sorry about that. I'll fix that in the. You know, you don't want to scare people off. Here's an input example. It's 1536 data
You can
points.
just run it for resolution anyway, because you have to work up to it.
Yeah. Okay, so that's there. And so yeah, let's just try a couple of quick exercises. But try in the anelastic case, just turning magnetism on and adjusting eta so that the magnetic Prandtl number is 2 and run for 10 time steps. Okay. And then for the non-dimensional anelastic case, change your Prandtl number to 2 and run for 10 time steps. This is actually kind of important because since we do just have 24 minutes, or 20 minutes, we're going to go ahead and talk about ensemble mode. So you want to make sure all 3 of these are actually running for you without crashing. And the ensemble mode portion will go pretty quickly. So if you want to just follow along with me, you can. So I'll go to the dimensional and set a magnetic Prandtl number of 2. So in the anelastic one, we would turn magnetism on in the physical controls name list. Then down at the bottom, I would set eta top to be 4.0 10 to the 12. By the way, you can use scientific notation here, just like you're programming in Fortran. And then I need to tell it to initialize the magnetic field. It looks like it's already set, so that's good. Okay. So I'll run that. Oops. And I forgot to move main input sign to main input. Okay. Notice here the preamble, it tells you about the reference state, right? It says we're using a polytrope, it's dimensional. And it tells you everything in its CGS units. And then it tells me that I turn magnetism on. Okay. So then I would go to the non-dimensional anelastic run. This one, we just want to change the Prandtl number to 2, right? And turn rotation off. Was that what I said? Okay. So we'll change the Prandtl number to 2 down here. And then rotation, we'll just turn that off. Notice, by the way, if we look back at this equation set, for the non-dimensional, so if you turn rotation off, your Ekman number is just acting like your viscosity here. Okay. Just when you turn rotation off, this z cross v term just disappears. Okay, so that's a little bit odd, but you can turn rotation off, but then your Ekman number is really controlling your viscous term. Okay.
So what you set the Ekman number to still matters.
Yeah, it still matters in that one. Yeah. So it's a little bit odd. That's why in my Boussinesque I non-dimensionalized based on the thermal time so that rotation didn't do strange things. But then you might ask, there's always a question, what should you do, right? So then I'll run this just to make sure. And what are they? Same deal. Oh, and it created some output. Ignore that, right? Okay. All right, so that's good. So did everyone get theirs to run? It's kind of important. All right, the next module we're just going to talk about ensemble mode, and it's pretty fast, and that's where we'll stop. And then after that, it's all just generating output and plotting.